make sure I hit record. So before we dive in, what I really want to show you is this study guide that I put up that is going to be really, really helpful for you going through the different drugs. And the way that I've set it up is that you have all the different drugs and the way that you can memorize them. So all the muscarinic agonists follow this pattern of oxygen, carbon, carbon, positive nitrogen. So you have oxygen, carbon, carbon, positive nitrogen. So the quintessential muscarinic agonist is um, acetylcholine. Is this going to open for me? There we go. Then, through medicinal chemistry, what we've done is we add different aspects to the drug, and that's going to change what the metabolism of the drug is going to be, or the absorption, or the distribution. And this is where you're going to go through and you're going to describe that. So, what is the effect of the methyl group? What is the effect of having swapping for the carbamate? What is the effect of doing the methyl group and the carbamate or the lactone, for example? So all you really need to do is memorize the backbone and then how the different modifications of the backbone cause the same changes. Now, what's really important to know is that if you have a carbamate in one drug, it's going to act exactly the same as a carbamate in another drug. So you don't need to memorize, oh, what does a carbamate in carbachol do? It doesn't, it does the same thing that a carbamate anywhere would do. So I highly, highly recommend going through and using this guide. Um, Same thing here, anticholinergic drugs. They all have an aryl group, AR, carbon, carbon, nitrogen. Aryl group, carbon, carbon, nitrogen. So this is your backbone, and then here are some modifications to the structure that cause different changes. So highly, highly, yes, aromatic group. Yep, good question. And we're going to go through a lot of this as well, different stuff like that. We'll talk about log P in a second. But again, the biggest thing is not necessarily focusing on one drug, one structure, but comparing and contrasting the different drugs in a different class. So, for example, the alpha 1 agonists all have this phenylethylamine backbone. So, we'll talk about this as well. You have phenyl ethyl group amine. So, if you have phenylethylamine, that means you're an alpha 1 agonist. So, and then the question is, what does the effect of having missing that fourth hydroxyl group mean? Does this make sense? Do people think this is going to be helpful for them? Okay. Um, if you go on the classroom and you go to the main post, um, which I think is supposed to be this one. Up, I'll post a new link. In the Gabe tutoring link is my filled in versions of all of these study guides. So if you're looking for what is ultimately, quote unquote, the answer to these different questions, you can find these. And I'll make sure that you can have a link in order to get them. Please don't just use use this as a way to skip doing the work. Um, you're not turning this in. This is just for you to make sure that you're have a study guide essentially. But I want to make sure that you have the information so that way, even if we don't finish today and it's going to take us a while to come back to it, um, you still have a way of accessing the information. And just so you know, exam 3, exam 4, and all of the second semester is the same thing. So this format, if you're able to work with it and make it make sense, is going to really, really, really help you. Any questions about this format? I only used these to study, and I think I got 90s on all of the exams, and other people who did the same also did really, really well. The hard part about MedChem is just organizing the information and figuring out what's important. And so the people generally don't have a very good chemistry backbone, and then they get frustrated with it. They don't really understand what's important and what's not important, and then you get the whole thing. They also don't come up with tricks like memorizing the backbones for themselves. So, um, no, you guys have to like chemistry because I tutored you in organic chemistry. He doesn't say right because he'll what he'll do is he'll give you a fake drug, and you have to be able to use the information that we're going to talk about today um, to uh, be able to understand that fake drug. All right. All right. So let's dive in now that I gave you the way to study. So, in the beginning of the packet is just a whole bunch of information that has been already explained to you in PCOL. So, I am not going to go over all the pharmacology information. Please see all the pharmacology notes that you have taken. Um, the that's where you're going to get all the uses and different stuff like that. What I am going to focus on is talking about the drugs and their modifications. All right. So the first drug that we're going to look at is probably one of the most important um, uh, structures in the body, which is acetylcholine. Acetylcholine is made up of two parts. When it's synthesized in the body, it is made up of a acetyl group. So it comes from essentially acetic acid. So actually, it would come as O minus, as acetate, and choline. And through the smashing of these two portions together, acetate, and choline, you end up with acetylcholine. Likewise, if you break down acetylcholine, you get acetate and choline. And remember that the enzyme that's doing this is acetylcholinesterase, which is going to be using primarily water in order to break apart the acetylcholine. So the big thing to understand about acetylcholine, and this is what I really want you to focus on when we talk about acetylcholine drugs, cholinergic drugs, is that this ester group in acetylcholine here we have an ester. This ester is easily hydrolyzed. Which means that the water that is used by acetylcholinesterase will degrade acetylcholine. So the first modifications that we can make to acetylcholine are different ways of either preventing acetylcholine from fitting into the receptor or decreasing the hydrolyzability of the drug. So, for example, when we look at the drug methacholine, I'll put this on a different color. Methacholine has the same acetylcholine backbone, but it has this methyl group adjacent to the ester. This extra methyl group is going to prevent acetylcholinesterase from wrapping its grubby little fingers around this drug and degrading it. So when you add a methyl group into a very, very central part to where metabolism happens, right? Here is the site of metabolism, and we're adding this methyl group so that way we're preventing metabolism. So when we look at the half-life of methacholine, do we expect methacholine to have a longer or shorter half-life than the half-life of regular acetylcholine? Longer. Exactly. You prevent metabolism, you are going to increase the half-life. Uh, da, 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 da. I had this figure. Yeah. In fact, just to show you what this effect is, this isn't something you need to know, but the half-life of methylcholine is about 24 days, whereas acetylcholine is about 6 to 13 days, depending on which neuron we're talking about. So you've almost doubled it. Pretty cool, right? It's just a simple modification. So one way of extending the life of acetylcholine is to add a methyl group. The other way is to work on that um, on the hydrolysis of the ester moiety itself. And this is where we get the drug carbachol. Carbachol is a bioisosteer. And basically what that means is that we have, instead of just having a regular ester, we have attached an amine, a nitrogen, to the other side, which creates the functional group of carbamate. Now, carbamates, so changing our ester into a carbamate, what this is going to do is it's going to increase the stability of the uh, of the oh god, not carbocation. Come on, Gabe. What the hell is that thing called? Carbonyl carbon of the carbon. And ultimately, what this is going to mean is that we have increased hydrolysis resistance. So, do we prevent hydrolysis completely? No. So, the carbonyl carbon here, remember that this is the site of hydrolysis. This is where the water in acetylcholinesterase is going to come in. And so having the carbamate is going to decrease the ability for the water to break apart the drug. So carbamate is way more stable than the regular ester acetate functional group. Um, da, da, da. What do we think? Who's gonna have a longer half-life? Carbachol or acetylcholine? Yeah, carbachol. The half-life of carbachol, I think, is somewhere around something similar. I think it's around 24 days as well. Um, I can't remember it off the top of my head. This is a really good question. Which is better, methacholine or carbachol? We can't really compare them. We can, I mean, that's not true. We can compare them, but in this class at least, we're not going to worry about that. In terms of, which is better, methacholine or carbachol. All you need to know is that either one would cause decreased metabolism. So what's the overall effect? The effect of methacholine is what's called steric hindrance, which is just a fun way of saying crowding. We're crowding out the ability for acetylcholinesterase to come in and metabolize the drug. What is the effect of the carbamate? Is we're increasing stability. Oop, this has an N in it. Steric hindrance. So ultimately, what this means is we need to combine the two of them. And create the drug bethanechol. Bethanechol puts together both the methyl group in methacholine and the carbamate of carbachol, and you get the best of both worlds. Anybody want to guess what bethanecol's half-life is?
24 hours?
I think it's closer to I think it's closer to I think it's able to hang around for about a month and a half. It's hard because this drug is used. So this actually brings us to yes, you're going to need to be able to identify the drug based on the structure. Yep. Luckily, he's not going to give you like if he gives you the structure of bethanechol, he's not going to give you bethanechol, carbachol, and methacholine is part of the question. He'll say, is it bethanechol, is it albuterol, or is it, morphine? So he'll give you drugs of different classes. He's not going to, overdo it. Which is why being able to identify the backbone, oxygen, carbon, carbon, and plus is so important. All right, let's talk about the last thing that ends up getting that's really, really, really important for these drugs. And that has to do with this positive nitrogen, which you'll notice is both present in the regular acetylcholine and in all of our other drug structures. So the methacholine, the carbachol, and bethanechol. So all four of them have the positive nitrogen, which is called the ammonium group. Remember that EM refers to positive charge. So here we're talking about a nitrogen with a positive charge. And a nitrogen with a positive charge is going to prevent absorption. Right? We know that only neutral drugs can get absorbed. So if you are giving methacholine, carbachol, bethanechol, and are they going to get absorbed through the membrane? Not at all, right? They're all constantly charged. N plus. So if your structure has N plus in it and you administer it as a drug, you're not going to be able to absorb the drug, which means that we're going to be using it for topical applications. Now, we're not talking about topical like skin, we're talking topical like eye. So you apply it as an eye drop specifically for glaucoma. So you're going to be able to change the accommodation of the lens, allowing for the aqueous humor to flow from the back of the eye to the front of the eye. But having this N plus prevents absorption, which means that you have minimal systemic effects. Does that make sense? Exactly. Localized effect. So on the exam, is it important for you to memorize just, oh, what's the structure of bethanechol? Not really. It's more important for you to be able to say, okay, I have N plus. I know that N plus is going to prevent absorption no matter what drug that's going to be in. Carbamate. Carbamate is going to increase the stability of the ester and decrease or increase hydrolysis resistance, no matter what drug it is it's in. So don't focus so much on the what's in the actual structure. Focus more on what the each component does, which is why I broke it down that way. All right, let's continue along. Last two drugs. And this is going to bring up some foundational points, and then we'll be right on our way. The next drug that we're going to look at is pilocarpine, which again is a cholinergic. It's a muscarinic agonist. And the functional group that we have here is the lactone. A lactone is a cyclic ester. So if we follow around the ester, we can see that the oxygen links back around to the carbonyl carbon. What this does is it adds ring strain to the ester, which ultimately increases, well, the better way to say it is that it decreases stability. So having the lactone as part of pilocarpine actually will increase metabolism because water is going to be more likely to attack that lactone and cause an issue.
So it would be easier for the pilocarpine to be metabolized by the to just be metabolized in general, right?
Sorry, my headphones died. Yes. So the pilocarpine, when the water comes in to attack it, the water is much more likely to break it apart. So if you see a lactone on any drug structure, that structure is going to be way more susceptible to being metabolized than anything else. So if you're comparing a regular ester versus a lactone, which is a cyclic ester, you are way more likely to metabolize this drug. Now, does pilocarpine have an ammonia atom? Does pilocarpine have that ammonium atom? No, it doesn't. So it's not present unless it's in certain conditions. Because what can happen is that this nitrogen, which has a nice lone pair on it, can end up bonding to a hydrogen, gaining that ammonium component. So it's not present normally, but can be formulated as such. So what this means is that if you had pilocarpine HCl, where the hydrogen from the hydrochloride is going to protonate that nitrogen, you're not going to cross the uh the um you're not going to cross into the blood, and you're going to have minimal systemic effects, which is where we get pilocarpine for glaucoma. If you have regular pilocarpine, something like do, 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 mm, mm, mm. No, we're not going to talk about that. That's going too deep into it. So just so the big thing to take out of this is that just because there isn't the nitrogen, the quaternary ammonium to begin with, doesn't necessarily mean we can't formulate it to come about. And this is where we talk about this other drug, cevimeline. So up above, we have pilocarpine. Down below, we have cevimeline. So let's talk about a couple of different things about I can never say this drug. Cevimeline. First of all, for for this drug, we have no ester or lactone, right? What functional group is this? We have an ether. Exactly. So if you have no ester, are you going to be metabolized through acetylcholinesterase? Not at all. So of all of our drugs, who is going to be the most stable? This one. Super, super, super stable. The other important part about cevimeline is that we have this sulfur here. And whenever you see sulfur, I want you to think increased lipophilicity. So is this drug going to be able to cross into the body? If you administered it into the stomach and into the intestines, would it cross into the blood? 100%. Two reasons. First reason is because just by itself, we do not have that quaternary ammonium, and we're using sulfur to increase the lipophilicity. In fact, it's so lipophilic, it's actually able to cross the blood-brain barrier. Is this purely because of the sulfur? No, there's a lot more factors that go on in terms of crossing the blood-brain barrier. But what I want you to know specifically about this drug is cevimeline does cross the blood-brain barrier. The reason for this is, I'll explain that in a second. The reason why it can cross the blood-brain barrier, which means that it's used in Alzheimer's disease, which is a hypocholinergic state. So in Alzheimer's, someone has decreased cholinergic signaling, and so using cevimeline allows for us to stimulate that muscarinic receptors in the brain. We got a really good question about why does it have this zigzag? It's actually because there is this is a bicyclic ring. So you have your chair, and above the chair you have this 2-carbon bridge. Yeah. Do you have to know that? No, you do not. But that's why there's this zigzag. Couple of questions for you. Of the muscarinic agonists, which one is going to have the most systemic effects? Cevimeline. Exactly. Why? Because it is most lipophilic and it's even able to get into the brain. Also, real quick, what functional group is this ring here in pilocarpine? This is a heterocyclic ring that you guys should be aware of. Exactly, imidazole. Very nice. Any questions about the muscarinic agonists? All right. Uh, now that we are moving on to other drugs, I'm not going to draw them purely because I am lazy, and watching me draw these drugs is not going to make this process any better. So I'm just going to copy and paste the structures. But if you are using the guide, um, then you should be all set. Is it? That's too small. Um, Let me zoom in. All right. Up next, we are going to be talking about the acetylcholinesterase inhibitors. All of the acetylcholinesterase inhibitors follow the same backbone. They have this nitrogen on one end. So the backbone, for identification purposes, is you have a nitrogen on, oops, sorry. It's actually, we're talking about which nitrogen? Yeah, other one. They have a nitrogen on one end, so nitrogen. Then they have an aromatic group, like the phenyl, and then an oxygen on the other end. So if you see N-aryl O, N-aromatic O, you know, okay, that's acetylcholinesterase inhibitors. Physostigmine is going to be our quintessential, our basic acetylcholinesterase that we are going to base things off of. First things first, acetylcholinesterase inhibitors should in some way mimic what structure? What do they need to mimic in order to inhibit acetylcholinesterase? Acetylcholine, exactly. So they should be around the same size and have the general characteristics of acetylcholine, right? And what did we see in acetylcholine? It had the ester, couple of carbons, and a nitrogen. And would you look at that, we have something very, very similar. We have an ester, couple of carbons, and a nitrogen. The problem is that we've made these drugs to be bigger and bulkier, so they sit inside of acetylcholinesterase and prevent it from doing its job. Now, couple of key factors about acetylcholinesterase. Move that down there. In order to attack acetylcholine, in order to attack the enzyme, the drug needs a carbamate moiety. So the function of the, oh, can you see this pink? Probably not. The function of the carbamate here, part of it is we are increasing stability. But the other function is it is essential for attacking the serine amino acid in acetylcholinesterase. So that carbamate attaches to serine and doesn't let go. Does that make sense? All right. These other nitrogens here, these are non-quaternary ammonium nitrogens. So can these drugs enter the circulation? Can they go into the blood? Can they get absorbed? Yeah, they can, right? So remember, these are not N plus, so these can get absorbed. All good. By the way, is this more clear than class? Than has he talked about it? Okay. All right. That's always my goal. So far we've talked about good things. Let's talk about why physostigmine doesn't do a very good job. And it has to do specifically with this attachment. The nitrogen benzene attachment is very unstable. Super, super unstable. It's not unstable due to metabolism. It's unstable because it causes detachment from the enzyme. So if you have in your acetylcholinesterase inhibitors, if you have this nitrogen benzene connection, you are going to cause the drug to detach, which obviously means that we have a reversible acetylcholinesterase inhibitor. So, in order to solve this issue, oops, what was created, is that too small? Probably too small. What was created was rivastigmine. Same thing, right? We have our N aryl group O. We have our carbamate, which is going to increase stability as well as provide serine attachment. What's your question? So what's the seal with Sarah? What? Oh. Why do we talk about serine? Good question. All good. Uh, Real quick as well, it's a non-quaternary ammonium, right? So this is not N plus, so it can enter into the circulation. So we have a really, really good question about why do we care about the serine and acetylcholinesterase? And what I'll do is I will bring up this diagram. And essentially what happens in acetylcholinesterase is that it has two sites to it. The first site is that it has a ton of negative amino acids, and those negative amino acids are attracted to the positive nitrogen. In order to correctly dock the position of, because attracting this positive nitrogen is super, super easy. But in order to dock the ester portion of acetylcholine correctly, we have the acetylcholinesterase is using serine to correctly dock it. Actually, here is a much better diagram. Here we go. Much, much, much better. So once again, the anionic site is using tons and tons of negative amino acids, aspartate, glutamate. That's going to help keep the nitrogen in the correct position, whereas the ester is using a serine moiety to attack our drug. And this is what's going to enable the water to come in and cause the issues and break apart acetylcholine. Does that answer your question? Exactly. Yep. Yep, yep, yep. So when we look at exactly. So when we look at physostigmine, for example, do, do, do. No, come on. Oh, don't tell me nobody. Oh, nobody has drawn it. Someone kind of did. I'll draw it. So what ends up happening with our acetylcholinesterase inhibitors is that they have something very, very similar where they're going after that serine site. So here we have our anionic site. And here we have our serine and its OH group that's coming out. And I'm going to draw another one over here just because I need to explain two things. So we have our serine. Coming out of it is the OH. So what happens with physostigmine or rivastigmine, which I'm going to draw this with rivastigmine just because it is a smaller drug. What ends up happening here is the drug acts in a way to bind to the serine moiety. What do I mean by that? What I mean is that the drug actually splits itself apart and it attracts the carbamate, almost like a suicide bomber. So what ends up happening is that we're going to cleave the drug in half. But the result is you have a serine that is permanently attached to that carbamate portion. And what we call this is a carbamylated acetylcholinesterase. So what is the important thing to understand about the acetylcholinesterase inhibitors here is that their job is to make the serine attach to the carbamate. If the carbamate does not stick onto the drug, then acetylcholinesterase can do its thing. This is why it's really, really, really important for the acetylcholinesterase inhibitors to have this carbamate moiety on it. And we're going to talk about a couple of different drugs in just a second. But does that make sense? Any questions about this? Okay, sweet. So going back up to rivastigmine, the last thing that I just wanted to talk about is that for rivastigmine specifically, there's no nitrogen benzene connection. So this is just going to mean that we have increased stability for attachment. So if we're going to make the drug attach better, then this is the same thing as saying is that we're going to decrease detachment, which is increase the duration of action. Right? We need that carbamate moiety to be stuck onto the drug or onto the serine. And so by not having a nitrogen directly connected to the benzene ring, we're going to make sure that the drug is stuck on there. Moving right along, the next two drugs that we have to talk about, which I'm just going to briefly go over, neostigmine and pyridostigmine, are all about increasing that nitrogen benzene attachment. So again, they both have the carbamate. That hasn't changed. Here, we're using them as quaternary ammoniums. So are you going to be able to administer this as a tablet? No. Which is why pyridostigmine and neostigmine are IV only. So you have your quaternary ammonium, IV only, purely because they do not get absorbed. But what we have going on in neostigmine is a different functional group. So this is probably the easier functional group to identify. What functional group is present in pyridostigmine? We do have the carbamate. How about the one in red? What heterocyclic ring is that? Pyridine. Very, very nice. We have pyridine. Pyridine is very, very stable. So that means that we are going to be decreasing detachment a ton. So pyridostigmine has a much, much, much longer half-life and duration of action than the previous ones. And this functional group is a little bit harder to see, but it is this functional group, aniline, which I would say is just stable. I wouldn't say it's, meh. It's kind of mid-tier. But again, it's going to be decreasing detachment, increasing the duration of action, increasing the half-life. All right. Let us talk about our last couple of things. I'm only going to talk about one of them, purely because the other one is exactly the same. Diisopropyl fluorophosphate. This is one of those the organic phosphate poisons that we talked about in P-col. And these are all of your irreversible acetylcholinesterase inhibitors. Good question. So what is going on here is that not having that nitrogen benzene connection increases stability for attachment. So we're increasing attachment at the same time we're decreasing detachment. So we are increasing attachment and decreasing detachment, which is going to increase the half-life. What is essentially going on here is that the phosphate is going to irreversibly bind to the serine in acetylcholinesterase. So we have our serine, and what ends up happening here is our phosphate gets stuck on in a super, super, super strong bond. Uh, So that the fact that there's this organic phosphate group in the molecule means that we're going to end up having this really, really, really strong bond between the serine and the phosphate. And so we get this irreversible group. One of the things that ended up getting developed as part of World War One is this guy. I think it was World War One, ecothiopate. And the all this is doing is, once again, what's the function of sulfur? Increase lipophilicity. Our quaternary ammonium here is going to uh, help coordinate binding. And so what you end up with is a very, very, very potent poison. And so part of the use of ecothiopate was you would just release it as a gas into the air. It would bind irreversibly and it would kill people. Nowadays, we use ecothiopate in glaucoma, but very, very dangerous. I think I'm thinking about the right drug. Very dangerous. All right, last drug we're going to talk about is donepezil. Donepezil, which is not donepezil. Donepezil, same thing, has the same N aryl group oxygen backbone. But donepezil specifically is a central acetylcholinesterase inhibitor. So we have no quaternary ammonium. So we're able to enter the circulation. But what do you notice is missing here that we should expect to have on acetylcholinesterase inhibitors? What is missing? No, we have tons of aromatic rings, right? We have a benzene ring here, we have another benzene ring here. Close, not an ester, but what is the specific group that we need? Not an ether. The carbamate, exactly. No carbamate. So what ends up happening with donepezil is that it does not bind to the active site. Which means that it is a negative allosteric modulator. So in other words, it's a non-competitive antagonist. Now, in order for it to get to this, when we talk about central, we're talking about entering or crossing the blood-brain barrier. And when you look, we have tons and tons of carbons everywhere, right? Lots and lots of carbons which are all going to increase lipophilicity. So donepezil can cross the blood-brain barrier, lots and lots of carbons. And does anybody know what donepezil ends up getting used for? Close, not Alzheimer's, but Parkinson's. Parkinson's disease. Oh, no. No, Parkinson's is dopamine. It's Alzheimer's. No, it also gets used in Parkinson's. It gets used in both. But in this context, we're talking about it in terms of its effects in Alzheimer's disease. Parkinson's, because it's balancing the dopamine acetylcholine seesaw, but we're not going to talk about that. All right, moving right along. I want to get through I think we should be able to finish it all. Maybe we'll need 2 sessions. We'll finish all the cholinergic stuff today. Something about the seesaw. Yeah, we'll talk more specifically about Parkinson's when we in the antimuscarinics. But it's especially once we talk more about Parkinson's next semester, I think, for you guys, if I remember correctly. All right, antimuscarinics. All of our antimuscarinics, their backbone is going to be aromatic group, carbon, carbon, nitrogen. They all follow this same sort of structure. The first one that we're going to look at is our quintessential. So the one that we're going to be comparing against, which is atropine. So you guys should already be able to tell me something very, very specific about atropine purely based on what I circled in pink. What do we know about atropine based on what I circled in pink? Exactly. We have an ester, which means that we're going to hydrolyze it. So, in other words, we have easy metabolism. Can you already think of a way to modify atropine to decrease metabolism? Hint, hint, get rid of the ester. What can you tell me about this nitrogen here, purely based on what we've talked about before? Yeah, it's non-quaternary ammonium. It's not charged. So this means it can enter the circulation. And specifically, atropine is able to cross the blood-brain barrier. One kind of Actually, I don't think atropine can. I would just say that it can enter the circulation. I think that's probably the better way of putting it. One of the drawbacks to atropine is that we have this primary alcohol. Primary alcohol. This primary alcohol is very, very, very hydrophilic, which means that we're going to decrease the lipophilicity of atropine. Can atropine cross? I think it can, actually. Cross BBB. I'll put it back. So let's look at a couple of modifications. First things first, we have ipotropium. What is the main modification of ipotropium? What got added here? Okay, perfect. It does cross into the BBB. Thank you. Yeah, we added a isopropyl group, which created a quaternary ammonium. So can ipotropium cross into the circulation or into the cross the blood-brain barrier? No. So we decrease absorption, which, if you guys remember from Picol, ipotropium is used primarily as an antimuscarinic for asthma. Exactly, it's an inhaler. So why does having this isopropyl group make it the best drug over atropine for an inhaler? What does this mean? Exactly. No systemic absorption or minimal systemic absorption. So if you had to give a patient atropine versus ipotropium for their asthma, which one are you going to give? You're going to give a drug that doesn't cross into the bloodstream and cause systemic effects. By the way, this is how the name came about. Isopropyl, atropine. And then ium for the quaternary ammonium. Right? So you have your N plus, your atropine, and your isopropyl group. By the way, a lot of drug names get that because of this. Moving along. And then, of course, I'm just not going to keep repeating it so we can kind of move along. Is it has an ester, so is it easily metabolized? Yes. It has the hydrophilic group, so it decreases lipophilicity. So all those different aspects. So I'm just not going to specifically point them out. Benztropine. What is the main difference between benztropine and atropine? What went away? We added a benzene group. Yep. But more specifically, exactly. What functional group is this? It's just an ether. So we modified our ester into an ether. What is this going to do to the metabolism of the drug? Exactly. We're going to significantly decrease metabolism. What's the other thing that got removed as part of the structure of benztropine? So the first thing that got removed was the ester. What's the other thing? The alcohol. So our primary alcohol was removed. This means that we're going to be increasing lipophilicity, which means that benztropine has maximum BBB penetration. So who is more likely to be used for a CNS disease? So say something like Parkinson's. Would you rather use benztropine, or atropine? Exactly, benztropine. The other aspect here that I should mention is that adding this other and second benzene, they're both going to work together to increase lipophilicity. So dibenzo, way more lipophilic. By the way, benzyl atropine. You guys are like, wow, drug names are so cool. How do they come up with these things? Nobody says that. I'm the only one that says that. Scopolamine. Scopolamine, going back, does have the ester. It does have the primary alcohol. It has a quaternary, it's non-quaternary, but what it has is this functional group here. And what functional group is that? Does anybody remember? What do we call that little triangle? Starts with an E. Good. Lactone is a good guess. Lactone requires us to have the double bonded O. Epoxide. Oh, dang. So the epoxide here, all we're doing with scopolamine is we're increasing BBB penetration. That's all it's doing. What's interesting is that epoxides have this weird property, if I remember correctly, that they just gravitate towards the brain. So the body basically sees an epoxide and is like, oh, get that bitch in the brain. Which is why really the only thing that scopolamine is used for is for motion sickness. because the body is like, oh, all right, epoxide, get it in the brain. Which now you guys will always remember about epoxides. Get that bitch in the brain. Um, which is how it was explained to me. If Mahana asks, I want you to explain it that way. All right. Uh, do, do, do. Ba, ba, ba. This is a better picture than the one I have. All right. The next drug that we're going to talk about is tolterodine, which again is an antimuscarinic. And essentially, what's going on with tolterodine is that um, it is mimicking the structure of atropine, but in a very loosey goosey way. And I wish I had a picture to really be able to explain it, but no. So for tolterodine, essentially what's going on is we have a lot of the similar properties, right? We have our alcohol, we have our benzene ring, and we have our nitrogen. And if you were to align these drugs over each other, what you'd find is that they have very, very, very similar, um, uh, very, very similar arrangements. That tolterodine can kind of uh, modify itself to look like um, atropine. Tolterodine, the kind of important thing here is looking at this isopropyl group here. And really, we're not going to be comparing, like, obviously, it doesn't have an ester, so it's going to be more stable and all that business. But really, when we look at the different comparisons of antimuscarinics that share a similar backbone, for example, we start to see where those differences are coming in. So here's tolterodine down here, and let's compare it against oxybutynin, for example. Specifically, I want us to look at the ethyl group in oxybutynin versus the isopropyl group in tolterodine. Oops. Oh, all right. Well, I posted it in chat. What is one of the phase one metabolic um, processes that could happen for either oxybutynin or tolterodine? What is one of the potential phase one metabolic pathways? So we have dealkylization. We have, man, I can't even remember half of them now. Um, we have demethylation, all those good ones. I'm just gonna bring up my cheat sheet. We have oxidation or hydrolysis. What's your question? There we go. So, uh, yes. Yep. Metabolism stuff is going to be on here. Yeah. And we're going to spend a lot more time on the phase 1 and phase 2 stuff just because we didn't have a lot of time previously. So using oxybutynin as kind of our basis here. What we have in oxybutynin is N uh N deethylation. Whereas in tolterodine, we have N deisopropylation. Yes. Yep. And you still have to know your heterocycles as well. So what's important to understand about tolterodine is that by increasing the branching of the N group, we're going to decrease metabolism, right? Remember that dealkylation likes very, very simple groups, right? It loves taking a methyl group away, or it likes taking an ethyl group away. But as we modify the structure of oxybutynin, we get more and more structures that that decrease that ability to snag a group. Compare this with, for example, solifenacin or darafenacin. Are we able to do dealkylation on solifenacin? No, right? You can't just snag a simple group off of solifenacin. So out of those three drugs, oxybutynin, tolterodine, and solifenacin, which one is going to have the lowest metabolism? Which one is going to be resisting metabolism the most? Solifenacin, right? Why? Because it doesn't have one of the pathways. Another thing that we should notice about tolterodine, though, is what do we remember about phase 2 and having OH, SH, or NH groups? So the phenol in tolterodine, what is this going to allow? Are we going to be able to do direct phase 2 metabolism on tolterodine? Yes. So if you were to make a modification of tolterodine, what would be one thing that you would remove from tolterodine? Yeah, remove the OH, right? And by doing that, we end up with propavarin. So propavarin is, I believe it was made after tolterodine, and it was a way to try to make it more resistant. Any questions about this? We're going to talk more specifically about metabolism later, but just in terms of comparing and contrasting, I just wanted to bring it up now. Different stuff like that. Okay. All right. Mm-mm-mm. Okay. Let's did he talk about log P with you guys? No? Okay. Then I'm not going to bring up log P. All right. How much time do we have? 15 minutes. Um, is it worth going into the adrenergic drugs? No, it's kind of better to talk about them all together. Yeah, well, all right. I don't want to dive into the next thing because I want to keep all the adrenergic drugs together. But we did finish half of the information on the exam, which I think is not bad at all. Um, like I said earlier, please, please, please go through the study guide that I put online. If you look, here's all the information that we talked about, right? In a very, very easy flashcard for you to understand. Put the drug name on one side and put everything else on the other. Would you look at that? I did it all for you. Um, you have to make flashcards for MedChem. You have to make flashcards. If you're not a flashcard person like I am, use Quizlet. Really, the only thing you need to do is you need to flip a card and go, oh, N-aryl O, perfect. That's a cholinesterase inhibitor. You flip the drug and you say, oh, aryl carbon carbon nitrogen, that's anticholinergic. That's how simple you can get these things in your head. Um, as we talked about earlier, all you need to do is just memorize what each of the different aspects does. Esters, easier metabolism. Having primary alcohol, less lipophilic, all those different things. So it's not so important to memorize what one structure or what one functional group does in one drug, but more how we compare and contrast those drugs over a group, just like we talked about. Um, he would ask things like uh comparing acetylcholine to methacholine, which would have the longer half-life. Or he would give you acetylcholine, methacholine, and bethanechol. So he would give you acetylcholine, methacholine. Actually, well, let's just say he gives you all four. So he gives you these four drugs and say which has the longest half-life, and you would say bethanechol. Exactly. Yep. So he's not going to ask you, what is a half-life of a drug? He's going to say, which one has the longer half-life, which one, um, yeah, exactly. What does it have to do with stability? What would it have to do with duration of action? That sort of stuff. The more stable, the longer the half-life. Exactly. Yep, yep, yep. No, you don't need to know the half-life. I think in my year, he specifically put them in that we did have to know, but I was looking through the packet and it doesn't look like that was a requirement for you guys. Oh yeah, it was bad. Um, a lot of people struggled. But um, does breaking down the drugs this way, does this make more sense than class at least? Okay, that's really the biggest thing I wanted to get across. Um, if you have questions, please let me know. I'm going to try after the MedChem exam, I'll put up some stuff about uh the like some MedChem questions. Um Wednesday we're going to do pharmacology, and then we'll probably have Monday we'll probably have another session over the weekend. I'll post the schedule. Yes, after the PCOL exam. Yeah, yeah, yeah. And then we need to dive into Thera as well. Uh, so we need one more session to finish MedChem, and then we'll probably need about 2 sessions to finish Thera. So I think we're in a good place. I'll post some videos, different stuff like that. All right, sweet. If you have questions, send me a message, and I will be around. What do I recommend to be in the flashcards? I can show you actually. Were these mine? No. I want do do do. So what I would have is the drug and the structure. And then what I did is I would say out loud the important parts from the let me go to I don't think I made them for the first semester. Um so it would have things like uh oh no, it would be it would come up the other way. Answer with yeah. So I would have it so that the front side was the structure, and I would say, okay, it has this, this, and this, which would cause this, this, and this, and then I would say, oh yeah, it's morphine. Um, and so okay, so this is codeine. Yeah, yeah. So honestly, just all the information that is in a row is what I would say. If you can get this on a flashcard, that's all you really need. Different stuff like that. Okay, sweet.